Hello, my name is Danielle Weinkoff, and I'm with Aging Aircraft Solutions. Today, I will be talking about how we developed a virtual environment in PlantSim to enable rapid digital and physical transformation. First, let's review the problem. The Warner Robins Air Logistics Complex has over 60 repair and overhaul processes it oversees. Management is looking to improve the productivity of their product lines, benchmark the process performance, and utilize data to aid in strategic decision-making. They're looking to move forward in their adoption and utilization of advanced manufacturing technology. Unfortunately, the Air Logistics Complex didn't have any existing process models nor easy access to systems storing process data. They have a manual data collection process and tight integration of process steps that add on to the daily challenges they face. The objective of this project focused on the development and deployment of a digital twin. We focused on a C-130 remanufacturing line to provide a platform for Industry 4.0 functionality. We aim to reduce investment in planning facilities, improve productivity of existing facilities, increase system flexibility, and build quantitative business cases for proposed process or facility changes. In order to achieve our objectives, we needed to understand the value of advanced manufacturing. It applies new technology, networking, and computer power to improve the manufacturing process. With foundations in both smart and digital manufacturing, advanced manufacturing allows for a fully integrated system to have model-based controls and estimations. In particular, we were interested in how we could leverage models or digital twins, sensors or network connectivity, and ways to increase the flexibility of the system. The project roadmap started with research into current operations and data collection methods at the complex. We then worked to develop a digital twin of the facility and virtual work instructions for each process step. We then shifted focus to virtual planning and commissioning analysis, and finally reports on those analyses. Our research started with collecting engineering knowledge of the processes and gathering data. Some of the engineering knowledge we utilized included assemblies and subassemblies, maintenance processes, part materials, and tolerance requirements. Once we had the data, we looked into data-driven methods and simulation approaches, including clustering techniques and optimization methods. The combination of these two allowed for the optimization of the process and virtual planning and commissioning. While we were completing our research, we were looking into ways to highlight project-specific benefits of having a digital twin. One of the most important ones we identified was the creation of a virtual asset that could be applied across the entire organization. Others included the reduction of planning time, improvement of communication of changes, and enabling virtual commissioning of new equipment or processes. From these benefits, we ideated potential use cases that could be addressed. This included monitoring by gathering statistical data on daily proceedings, maintenance by improving utilization of reducing asset downtime and lowering overall maintenance costs, training, communication by creating end-to-end visibility of the enterprise, and strategy and experimentation by verifying and validating concepts upfront. In order to build the data-driven digital twin, we chose to utilize plant simulation. This was due to the fact that we could conduct discrete event simulations and experiments, as well as our customer already having Teamcenter licenses available to them. The advantages of this program were mapped easily to our potential use cases as well. Some of the advantages PlantSim provided were virtual experimentation, simulations being based on the input data, high mobility and variability of cell placement, graphically representing data outputs, and having a data-driven decision-making process. Plant simulations features also allow us to utilize items like laser scans of facilities and 3D models we already had on hand to provide a real view. It also provides a platform for which things like plant layout analysis can be easily conducted. Similarly, the virtual manufacturing tool we created is layered for different functionalities and use cases centered around the manufacturing process. First, we laid the groundwork with process step data for the cells. Then, we made an overview of what process step simulations would look like. On top, we placed our 2D process flows, and finally, the 3D visualizations were added. This provided the environment in which we could conduct virtual commissioning and plant layout analysis. Here's a view of the 2D process flow map we created of the remanufacturing line. There are three main propeller parts that we mapped. The yellow line on top is the lever assembly flow. The green line is the flow of the propeller barrel, and the red line shows the path propeller blades take. We purposefully mapped these stations so that a process engineer can easily understand the flow of information and materials. Once we were able to understand the flow, we mapped process steps to their respective locations across the building envelope of the Air Logistics Complex. As you can see here, the paths cover far distances between several different buildings. The next step for us was to collect point cloud data. In order to do this, we took laser scans of the overhaul process line we were mainly focused on, different areas of the three buildings, and general use areas deemed important by the Air Logistics Complex stakeholders. We combined laser scan with work cells to the virtual layout, connecting them to the 3D visualization. Let's zoom in to this area here. This is an example of how we overlaid the scans with the layout. The source and disassembly and cleaning cells were placed first. Then the point cloud was overlaid. The point cloud is a single unattached assembly with no equipment modeling representing the cells. While this was a good first attempt, we weren't satisfied with the level of realism. So we iteratively explored other ways to raise the level of fidelity. The way we achieved our highest level of fidelity was by connecting the point cloud data to 3D models of the equipment and cells. Due to a large majority of the blade overhaul process steps located on the left side of Building 140, we decided to fully implement the point cloud data to that area. Here's a close-up of the blade machine shop. So each piece of equipment that we're looking at is not only a 3D object, but also has a point cloud overlay attached to it. This level of fidelity was found satisfactory as it could allow us to easily visualize changes in the environment. The total time to complete this environment was about 4 months. The first 2 months were dedicated to research while we scanned and compiled point cloud data. The next month was dedicated to encoding the 2D process flow map and building models of equipment. Finally, we used the last month to map locations of the process steps and increase the level of fidelity. To help us effectively deploy the platform, we mapped users to functions. This included, but wasn't limited to, production, scheduling, engineers, management, and plant services. These functions build up a use case for which the virtual manufacturing tool platform can address. After receiving the results, the information flows back towards the user. One of the general use cases we've addressed with the virtual manufacturing tool is performing what-if analysis to predict impact on process cells and the overall process line. In this case, a process engineer We'll review baseline validated plant simulation metrics, make changes to the process cell parameters that are being considered in the what-if scenario, evaluate the scenario results and compare them to the validated baseline. Then the value of the change is calculated. Results are then presented to engineering and production leadership for approval, modification, or rejection of proposed change. A second use case we've deployed the virtual manufacturing tool for is understanding the impact of adding, removing, or changing equipment locations. In this case, an engineer will document a desired outcome and define a study to include different constraints and limitations. We will then plan changes to the 3D environment to test these hypotheses and determine alternatives. Focused on these two use cases, we have completed several experiments to date. Here, I've highlighted some experiments that were of great interest to the Air Logistics Complex. Most of them support the production rate improvement initiatives that the Air Logistics Complex has been focused on. The first was looking at the effects of adding another machine to a process. A second was determining the optimal number of work-in-progress blades. The third was determining a better flow for the blade machine shop area. And the last was space availability for new equipment being visualized. We were able to provide in-depth analysis for each experiment and provide meaningful results for the customer. Moving forward, we are looking to further the virtual manufacturing tool's level of data integration. This includes utilizing new AR/VR technology, improving AR cloud accessibility, providing information overlays and visual analytics, and effective skill training in the virtual environment. This concludes my presentation. Please feel free to reach out with any comments or questions that you may have regarding this presentation. Thank you. This concludes my presentation. Please feel free to reach out with any comments or questions that you may have regarding this presentation. Thank you.